Yep, welcome back. All right, today we're going to look at limits of polynomials specifically as x goes to either positive or negative infinity. So we start with the general polynomial, right? This is like the mold to create any polynomial. You have all these c's, c sub i's as we say, where they're coefficients on the x, and the very last one represents the constant. And then you have, the variable x here, and it has powers. And so the c's can be any real number, but the actual powers, the exponents, they're going to have to be positive integers. And that's what this crazy little symbolage is right there. Don't worry about it if you don't remember that. All right, so let's do it. So let's take the limit of a polynomial. So it should be pretty easy to do a limit of a polynomial because it's just a sum. And you know the limit of a sum is the sum of the limits. But watch what we do here. All right. Can you figure out what I did from this line to this line? All right. Hopefully you say, oh, you just factored. In fact, I pulled out an x to the n. So that means if I was to multiply this x to the n to everybody, distribute it, right? Multiply it back out, I should get this. So let's just take a look. X to the n times c sub n, that's going to be c sub n x to the n, right? I get it. This might be a little wacky for you, but let's think about it. So the coefficient's not changing. That's just the number, like 5 or 3 or -2. So that has to be there. But why is it divided by x now? Well, x to the n times this coefficient divided by x. What happens when I divide monomials with the same base? What do? Subtract the exponent. So you would actually get x to the n minus 1. That's one way to think about it, right? I actually went and did the next coefficient here just to kind of drive home the point. X to the n times this. Notice the power here is now x squared in the bottom. When I subtract n and 2, I get n minus 2. And I can do that pattern forever all the way down to here. This one might be a little bit bananas, right? When you do n minus parentheses n minus 1, you're going to get x to the 1. So you're still subtracting the powers there. And then this one's a little easier. You do x to the n divided by x to the n, that's just going to cancel. You're just left with the constant there. So now why did I do that? Why did I do this craziness of factoring out the x to the n? Well, I'm doing a limit to infinity. So now think about this. All of these terms here have a divided by x. So they're basically constants over an x, right? Constant over x squared, be constant over x cubed, and so on and so forth, all the way down to constant over x to whatever, and then constant over x to that highest power, right? Well, what's happening to x? It's being driven to infinity. So all of these are going to be going to 0. They're going to be like not negligible, so to speak. Okay? And it doesn't matter if I'm going to positive infinity or negative infinity. We talked about that the other day. I'm still going to get a number that's getting smaller and smaller and smaller. I just might be going to 0 from the other side, but we don't care about that. We just care that these are going to 0. So if they don't mean anything, if the bulk of this problem then has nothing to do with these terms, I can say, all right, well, these are the only ones I care about, this x to the n times c to the n. So I end up getting that the limit of this expression here is actually equivalent to the limit of just this. And then I just wrote that out in one line so you can see it. The limit of this polynomial, and that's what this is right here, right? This is the mold for any polynomial. The limit of this polynomial as x goes to infinity is simply equal to the limit of this. Now, what is this? Specifically, we call this the end behavior model, which kind of makes sense because limits to infinity are talking about extreme right end and extreme left end. So this function is going to model that behavior, all right? More generally speaking, we can say, hey, this is the term of highest degree. So basically, the term of highest degree in a polynomial is going to be your end behavior model. And you're going to want to use that when you do the limit as x goes to infinity. Right now, notice if this would have been as x went to 5, then I could not have written this, okay, because these wouldn't be going to 0. So this end behavior model thing is only going to be a tool that you use if it's a limit as x goes to an infinity. All right, so that's a little proofy. Let's just do some problems, and I think it's going to make sense. All right, so here we go. So let me do the limit of this as x goes to infinity. Well, I notice this is a polynomial. It's a polynomial of degree 4. You're like, well, where's the squared term? Well, that's like the coefficient 0 there, right? We talked about that. So then if I want to do the limit of a polynomial as x goes to infinity, I have to identify the end behavior model. Well, the end behavior model is the term of highest degree. This is my end behavior model. Right? I'll say EBM. All right, that's my end behavior model. So that means that I can rewrite this limit as the limit of the term of highest degree and behavior model, right, as x goes to infinity. And all right, so what do I get there? Well, to do this limit now, you got to think x is going to infinity. It's growing without bounds. So let's just for a second, even though this is not 100% the way we should probably mathematically think about it, but you know what? Yeah, maybe we should. Think of infinity for a second as a really large number, right? I know it's not a number. Just think of it as a large number. If you take a number, a really large positive number, and you raise it to the fourth power, you're going to get a really large positive number. And then you multiply it by 7, you're going to get a really large positive number. Oh, okay. So then as x goes to infinity, 7x to the fourth is also going to go to infinity. And I'll drive home the positive by just writing positive infinity. And that would be my limit of that polynomial. Now that's pretty neat because that tells me that as the graph, as the inputs go that way forever, right, this graph is going to go up, which means it doesn't have a horizontal asymptote in that direction. In fact, you should kind of know that the polynomials don't have horizontal asymptotes. Why am I talking about horizontal asymptotes? Well, because yesterday we said to find the horizontal asymptote of a function, just take the limit as x goes to infinity. Well, we just did that. And I didn't get 7. I got infinity. So that means there's no HA. All right, let's take a look at this guy. All right, we'll bust out blue this time to make it more exciting. So now what's this? This is a polynomial in the variable y, right? It would fit that mold. It's a degree 3 polynomial. So I want to take the limit of it as y goes to negative infinity. Well, this here, guys, is the key. This tells me use an EBM. If it was as y went to 5, I wouldn't be doing that, right? I would just be plugging 5 in. But because it's y is going to an infinity, use an EBM. What is the EBM? Well, I do a little scan here. I'm like, all right, that's the term of highest degree, which makes sense because for large positive or large negative values of, in this case, y, this will be the term that carries the most weight, that dominates. These will be negligible, right? And so I'm going to rewrite this now as the limit as y goes to negative infinity of 4y cubed. Right? And that EBM, you have to take everything, the coefficient as well. So now how would I do this limit? Well, again, I would think for a second. I'm going to pretend like infinity is a really large negative number. Notice I said pretend, right? So, okay, put a large negative number in for y. Cube it. What do you get? You get a large negative number. All right, multiply it by 4. You still get a large negative number. So as y goes to negative infinity, 4y cubed goes also to negative infinity. Now, these don't always match up, guys. All right, you actually have to think about it like I'm thinking about it. Now, what does this mean? Well, basically means is y goes to negative infinity. If this would have been an x, say, I know I did y just to mess with you, but if it would have been an x, graph would be going down forever as I look to the left forever. All right, let's do the next one. In fact, you should do it, right? You should pause the video and you should try and do that one on your own, right? Now that you're back after pausing it, a little lawnmower in the background, hopefully you can hear that. Let's do it. So it's the limit of this, and you're like, whoa, wait a minute, this is a polynomial of a certain degree, right? Fits the mold. Might not be in order, but it certainly fits the mold of a polynomial. We have positive integer exponents. And I want to do the limit as x goes to negative infinity. Well, again, this here is the key. This tells you to use an EBM. Did you identify the EBM? Now, you may have said, yeah, it's 400x to the fifth when you did this because all of the other ones are in the front, but that's not true. Notice I tried to trick you. I threw it out of order. The EBM is the term of highest degree, and that includes the coefficient. So the term of highest degree is this guy, right? X to the seventh. That's the highest power. This is a polynomial degree 7. So when I go to rewrite this, it would be the limit of the end behavior model, right, as x goes to negative infinity. And you might also have said, all right, so my answer can be negative infinity. Well, again, think about it. Think of negative infinity as a large negative number. What's a large negative number raised to the 7th power? It's a large negative number, right? I'm following the order of operations, by the way, right? You got to do exponents before you multiply. So a large negative number to the 7th power is a large negative number. Now multiply by negative 3. Oh, that's negative times negative. That's positive. So I'm going to get a large positive number. So this is going to go to positive infinity. So in other words, if I was to look at the graph of this polynomial, as my inputs were driven to negative infinity to the left, this graph is going to be doing that. okay? Again, doesn't have an HA, right? So we're seeing the extreme left and extreme right hand end behavior depending on the limit that we actually do here, okay? All right, so pretty simple. All right, one point I want to drive home is that are we saying that this function is equaling that function? Because I don't think they're equal, right? So let me give an example using Desmos here. All right, so if I pull up a Desmos graph, I have two polynomials here. I have 2x cubed minus 5x squared plus x plus 2. I graph that. That's the purple one. This guy right there. All right, and then I have 2x cubed. Now, 2x cubed is the end behavior model for this polynomial function here. Do they look equal to you? Hopefully you're saying, no, they don't look equal at all. So then why can I write that the limits are equal? Well, what is the same about them? The functions themselves are not the same, but what is the same? And hopefully you're saying their end behavior is the same, right? So as x goes to positive infinity, both of these functions go to positive infinity. They go up forever. And as x goes to negative infinity, both of these functions are going to go down forever. And that's the kind of the idea of using end behavior models. So moral of the story, if you're doing the limit of a polynomial as x goes to an infinity, use an end behavior model. What is the end behavior model for a polynomial function? It's the term of highest degree. All right, that's not what it is for every function, but for a polynomial it is. All right, be good.